We are going to talk about orbits and platform presented by Mrs. M. Muthulakshmi, Assistant Professor, Department of ECE, King's College of Engineering, Bangalore. Remote Sensing, Unit 3. The topic is orbits and platform. Gravitational field and potential. On the diagram of gravitational field and potential energy, first one is the circle form. It's connected to sun and earth, and the formula is given by Ug is equal to gm1 and gm2 divided by r. m1 is the mass of the energy and m2 is the mass of the earth. R is the distance of separation between sun and earth, and g is the universal gravitational constant 6.67 into 10 power 11 m power meter squared kg power minus 1 and s power minus 2. The gravitational field and potential are fundamental aspects of Earth's geophysical environment that influence remote sensing, measurement, and data interpretations. And the concept is crucial of accurately analyzing remote sensing data and extracting meaningful information about the Earth's surface and subsurface features. Influence on satellite orbits. The gravitational field of Earth aspects of orbits satellite used in remote sensing missions, and satellites orbiting the Earth experience gravitational forces that determine the altitude and velocity. And variation in the Earth gravitational field due to uneven mass distributions, for example, mountains, ocean, and variation in the density of underlying geological structures, and affecting their stability and accuracy in acquiring remote sensing data. Geomodeling. The geo represents the equipotential and surface of Earth gravity at the equipotential surface of Earth field and best fits of global mean sea levels. It serves as a reference surface for measuring elevations and understanding the Earth shape and gravity field. Next one is remote sensing techniques such as satellite gravity and altimetry and employed and precisely measure variation in the geoid. The measurement contributes of refining geoid models which are essential for geotic applications of including mapping, navigations and geophysical studies. Gravity anomalous. Gravity anomalous are deviations from the average gravitational field of the Earth and are indicative of surface and geological structures and such as sedimentary basins, volcanic features and mineral deposits. Remote sensing technologies such as satellites gravity, airborne gravity surveys and used in map gravity anomalous with high spatial resolutions and data aid to geological mapping and mineral explorations and understanding the tectonic process. Next is subsurface characterization. Gravitational data when integrated with other remote sensing data sets. Example, multispectral imagery and radar data can provide valuable insights into subsurface characteristics such as density variation and groundwater resources. Next, gravity surveys combined with geological inversion techniques and enable the estimations of subsurface properties and delineations of geological structures and facilitating resource explorations and environmental assessments. And another one topic is escape velocity. Escape velocity is the concept of physics referring to the minimum velocity an object needs to escape the gravitational pull of a massive body such as planets or moons without being propelled further by additional forces. In the context of remote sensing, escape velocity is not directly relevant because remote sensing typically involves objects such as satellites or drones that are intentionally placed into orbit around Earth rather than being launched into space or escaping Earth's gravitational field entirely. Next one, escape velocity is minimum speed on object must have a break free from gravitational pull of a planet, moon or other celestial body without requiring any further propagations. And another one point, escape velocity is independent of the object mass. It decreases for smaller or less massive planets. It increases for larger or denser planets. On the moon's escape velocity is 2.38 km per second, much much less than Earth. It depends on the mass and the radius of the body is being escaped. Escaped from formula is given by v is equal to 2 root of q divided by r. V is equal to escape velocity. G is the universal gravitational constant, 6.674 into 10 power minus 11 nanometer square divided by kg power minus 2. M is the mass of the celestial body, or is the radius of the celestial body from center to point to escape velocity. Example, Earth for Earth, M is equal to 5.97 into 10 power 24 kg, R is equal to 6.37 into 10 power 6 meter, V is equal to 11.2 kilometer. That means the spacecraft must travel at least 11.2 kilometer per second, about 40,320 kilometer per h, to escape Earth gravity, ignoring air resistance. And another one topic is Kepler law of planetary motion. Kepler law of planetary motion are set of three fundamental principles describing the motion of planets and other celestial bodies around the sun. While this law are primarily concerned with dynamic of celestial bodies in the solar system, they have implications for remote sensing, particularly in the context of satellites, orbits, and orbital dynamics. In this diagram of Kepler law of planetary motions, first law, and then second law, third law diagrams. The Kepler first law, and another one of the name law of ellipse. It states that orbit of planets around the sun is on ellipse with the sun at one of the two foci. In the context of remote sensing, satellites can be placed into various. And another one, Kepler's second law, law of equal areas. The Kepler's second law states that a line segment joining a planet and sun sweep out equal area during an interval of time. Next one is Kepler third law, and another one name is law of harmonics. The Kepler third law states the related to orbital period of a planet or satellites to its average distance from the sun and the central bodies. Specifically, the square of the orbital period is proportional to the cube of the semi-major axis of orbits. Thank you.